All right, we're going to start chapter 2 now with 2.1, and this is going to actually get us into doing the calculus stuff. So let's get going on this. We're going to start with rates of change and tangents to curves. A lot of people give Isaac Newton credit for this, but it was actually Galileo that discovered that a solid object dropped from rest while not moving. Basically, you just hold it there and you let it go. It's going to fall a distance proportional to the square of the time it has been falling. So to the square of the time it's been falling. Basically, if you go take physics class, you're going to see something that's going to look something like this. Or even a lot of times they might make that A there and make it a G, and they call it the acceleration due to gravity. And what it was found to be is that it was this, 1/2 times 32 feet per second squared. That's that acceleration called the acceleration due to gravity, and then t squared. And it looks like that. Now, if you're probably in physics class, you probably got 9.8 meters per second squared instead of the 32 feet per second squared, but sticking with what the book does here. Because the 9.8 meters per second squared, that's the SI unit. But anyway, what we ultimately end up with after you take this, you can take half of 32, is you can basically get that y is equal to 16 t squared, and that's going to be in feet. And the reason it's in feet is because if you look at the units for this acceleration right there, it's feet per second squared, and then it's getting multiplied by time. And we're doing time in seconds, so it's time squared, so it's second squared. And as far as the units go, they all cancel out, and the only thing you're left with is the unit of a foot, which is a distance, which is what we want. So the distance something falls in time t is 16 times that time squared number of feet. Okay? And 16, it's about the approximate constant proportionality near Earth's surface. If you go to different places around the world, it's going to vary slightly. But it's pretty close for just about everything you want to do, and it's typically good enough, kind of a measurement for all practical purposes that we want to do. All right. So a moving object's average speed during an interval of time is found by dividing the distance covered by the time elapsed. So this is going to be our average speed. Okay, average speed. So what we're saying is if we have some graph here, right, where this is our position and this is our time, then if, say, we move on a curve that does something like that, and we want to know what was our average speed, well, what we can do is pick a starting point, pick an ending point, essentially connect them with a straight line, and take the slope of that straight line, and that will give us our average speed, and it's going to equal our change in position divided by our change in time, where if we look like this, this would be y1, this would be y2, position 2, this would be time 1, and this would be time 2. And so what those little triangles there mean, that just means change in. And so this would be, every time you do that, it means final minus initial. So the final is going to be 2, the second one. So second position minus first position, or final position minus initial position, over second time minus initial time, or final time minus initial time, or 2 minus 1, or whatever. But that's what those little triangles out in front of there mean. It's a Greek letter delta, so delta y over delta t is how that would be read. And that's change in position over change in time. So it's always final minus initial whenever you see that. Delta x would be x final minus x initial. So let's take a look here at an example. Average speed. A rock breaks loose from the top of a tall cliff. So here's our tall cliff. Okay. And this rock breaks loose and goes and starts falling. And it's going to fall all the way to the ground. What is its average speed, A, during the first 2 seconds of fall, and B, during the 1 second interval between second 1 and second 2? So if we go and work on this one, we can say that y as a function of time, position as a function of time, is what we had on this page, which was the 16t squared feet. Actually, you know what I'm going to do? I'm going to change it to what you're probably most likely to see in your other classes, which is meters per second squared. Just so it's not so confusing when you get there and suddenly everything changes. So that's half of 9.8, right? That's 1/2 times 9.8 meters per second squared is the 4.9 meters per second squared. So that's where that comes from. So if you go take physics, it'll look the same. Let's just do that. Okay, that's from the 1/2 g part. And let's do this. Let's make this just a little nicer. I just don't want you to get confused when you go to your other class. Let's have some consistency. GT squared 1/2, put a t squared, and then an equal, and then another t squared over here. So that's what it's going to look like most likely for you. Okay, so in part A, we're going with SI units here. Delta y over delta t is equal to y2 minus y1 over t2 minus t1. Change in position over change in time. So that's what that one's going to look like. Well, our positions are going to come from this equation right up here. All right, so we need y2, or not y2, we need y of t2, so the position at time 2, minus the position at time 1, so that's like an f of x. It's y, it's this equation up here with t2 plugged in, and this equation here again with t1 plugged in, divided by t2 minus t1, and then basically what that's going to be is y of 2 seconds minus y of 0 seconds over 2 seconds minus 0 seconds. Be sure to always include your units when you do these. Very important. Okay? And so that's what our T1 was and T2 was, because it started our timer. We started right when the rock broke loose, and then we wanted to know how what its average is during the first 2 seconds. And so we go back and plug this in. This will become 4.9 meters per second squared times 2 seconds squared minus 4.9 meters per second squared times 0 seconds squared. So you know that's going to just be 0 over 2 seconds minus 0 seconds is just 2 seconds. And then 4.9 times 2 is 4.9. Yeah, here's what we end up doing. We have 4.9 times 2 squared divided by 2. So what we can do is like cancel out one of the 2's, so it's not like a squared anymore, and one of the seconds to get rid of that second squared. And so we end up with this just basically 4.9 times 4 divided by 2 ultimately is 9.8 meters per second. So in the first 2 seconds, we have an average of 9.8 meters per second, which is the same amount as our, well, at least it's the same number, 9.8, as what we had for our acceleration, but it's not the same because this is meters per second. It's a speed. The other one was meters per second squared. It's an acceleration, so don't get it confused. And so that happens here with 2 seconds. For part B, it asks, what about during the interval from 1 second to 2 seconds? So essentially, we do all the same things here. I can write this whole thing out again, right? So I could take and I could just copy all of this. So I'm going to circle it all. I can copy it all. It's getting too much, but copy. Let's see if I can paste it here. Paste. Right, I'm going to put that here. And I'm going to get rid of that little extra charge rectangle there. Get rid of that. I didn't mean to copy that. So I can copy this whole thing here, except I need to make one change. I'm not looking, you know, my T1 is the same, except I'm not looking at 0 seconds anymore. All right, we're looking at 1 second. Okay, so that's going to be the big difference here. Like this over here is not going to go to 0. It's 1 second. And this down here is 2 minus 1 now. So this is 1 second. Okay? And so when we do that, what ultimately ends up happening is we have 4.9 times 2. That's going to be what, 19 points times 2 squared. I got to put my square back in there too. Squared. Okay, so that's 4.9 times 4, that's 19.6. And then we have 19.6 minus 4.9, and that ends up being 14.7. And then again, this was squared. We have a second squared canceling with a second squared, and then we have the seconds canceling with the second squared, and that second, because of the square, cancels with that second squares, and we have meters per second left. So same units, meters per second. This is the average speed during the from 1 second to 2 seconds, and this is the average speed from 0 seconds to 2 seconds. And it should make sense that 0 seconds to 2 seconds is a slower average speed because it started from rest, and it started off more slowly and it hasn't sped up as much yet. All right, let's take a look at this one. Instantaneous speed. Here, we want to find the speed of the falling rock in example 1 at time equals 1 second and time equals 2 seconds. Not between 1 and 2 seconds, but right at them. And so basically what we want to do here is take a look at it in a slightly different light. The idea is instead of looking at what we were doing was, we have some position and time graph like this, is instead of looking at a long distance, what we want to do is look at kind of a short distance between the two that are really close together, T1 and T2. Okay, and so we're going to do that by starting with, again, our y of t equals 4.9 meters per second squared times t squared. And we want to look at the velocity at t1. And the way that works is change in y over change in time, change in position over change in time. And what we want to do this time is, instead of doing a big step, what we're going to do is we're going to look at t1, we'll call that t1, and this will be y1. And what we're going to have is we're going to do a little step. So let me zoom in on this. We're going to do a little step this way, and we're going to step an amount h, which means this position right here is t1 plus h, okay? Because say we were at time 1, say time 1 was 6 seconds, and then we'd go and we'd add h onto it. So h was maybe, a tenth of a second. We'd be, instead of at 6 seconds, we'd be at 6.1 seconds. We'd be a tenth of a second further along. And then the corresponding y value would be, so this one, not just being y1, this one would be, this would be y of t1. This one's going to be y of t1 plus h. Okay, so we're going to get something like that, where we're looking at two kind of close together points. And so what I can do is come back over here, and I can make this, instead of just that, I can say, all right, it's change in position. So this is y2 minus y1 over t2 minus t1. And remember, y2 is y of t1 plus h minus y of t over t1 plus h, that's t2, minus t1. Okay? And we'll get something like that. And then what's going to happen is, look, we have t1 minus t1 in the denominator. Those are going to cancel, and we'll be left with just an h in the denominator. And so we can start plugging some numbers in. And so what we'll end up with is 4.9 meters per second squared times t1 plus h squared minus 4.9 meters per second squared times t1 squared, okay, all divided by h. And then what we can do is actually start squaring all this out and doing all that. So we get 4.9 is on both of them, so I'm going to just bring that out front, 4.9 meters per second squared. I'm going to bring that all the way out front. And then what I'm going to do is multiply by t1 plus h, and I want to square that. So that's going to give me a t1 squared plus 2t1h plus h squared, just like that. Then what I have on the next part is just the minus t1 squared. That's from right there. And that'll give me that, all divided by h. Now I'll notice that I have t1 squared and a minus t1 squared, so those will cancel. And then I have an h in everything. This has an h, this has an h, and so I can cancel that h out with that one and get rid of that squared. And what I'm left with is 4.9 meters per second squared times 2t1 plus h, just like that. Okay? And now what we want to do is we want to take this idea, our first little introduction to it, and it's the idea that we're going to get into here soon, is the idea of taking a limit. And what I want to do is basically pretend that h is really, really small, right? What we want to say is like kind of what we did before, as h goes to 0, this idea. We want to make h really, really small so that t1 plus h is like, 6 seconds and then 6.000000000, whole bunches of zeros and then a 1. So we've moved like to the next closest little point in time we could get. And as h goes to 0, our answer will go to 4.9 meters per second squared times 2t1, because that h will become so small, it's not really going to matter there. We have 2t1 plus h, and h is like point, we're letting h go to like 0.0000000, infinite number of zeros, and then like a 1. We're letting it go to something really, 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 really small. Okay? And when that happens, it's very insignificant. And what we end up with is 9.8, that's 4.9 meters per second squared times 2, 9.8 meters per second squared times t1. All right, and you may see this, then this is our v of t for whatever time we're picking. This was v of t1, and we can generalize this. We could have done any t we wanted, so v of t is 9.8 meters per second squared times t. All right, and you'd see this probably, if you see this in your, your physics classes, it'll probably look more like something like here. I'll write it right here. It'll be like v of t equals g times t, something like that, where that 9.8 is g. And we'll see it that way. And so we want the speed at 1 second and at 2 seconds, so we just have to use this equation and plug in those times. So v of 1 second is going to be 9.8 meters per second squared times 1 second. And so that second cancels with one of the ones in the denominator, leaves us with meters per second. This is 9.8 meters per second, which is exactly what acceleration is telling us. It's telling us 9.8, we're going to increase speed 9.8, right? Our acceleration tells us we're doing 9.8 meters per second every second, which is where we get that 9.8 meters per second squared. It's a meters per second per second. All right, so every second that goes by, we increase by 9.8 meters per second. All right, and so if we started at 0, 1 second later, we'd have to be going 9.8 meters per second. And 2 seconds later, well, we have 2 seconds, so it's 9.8 plus 9.8. We should get 19.6. And so this is 9.8 meters per second squared times 2 seconds, which is going to be the 19.6 meters per second, because we increased, we were at 0, we went to 9.8, and then another second went by, so we increased another 9.8. That's the 19.6. All right, so that's how that one basically works for you. And then next, we're not going to mess with this page here. And then we'll go over here. Average rates of chains and secant lines. I think I will do this in the next video just so this doesn't get too long. All right, so we'll start there in the next one.